Welcome back, Trigonometry, to part 2 of the Law of Sines lesson. In this portion of the video notes, we're going to be talking about something called the ambiguous case for law of sines. If you remember in a previous lesson for inverse functions, we talked about how inverse sine actually does exist in 2 quadrants, even though we restrict it to quadrant 1 only. So imagine for positive values of sine, you really get answers that could be from 0 to 90 degrees, or answers from 90 to 180 degrees that have the same value of sine. Well, triangles exist up to 180 degrees, which means whenever you use inverse sine to solve a triangle, you bring up the possibility of having more than one solution. One with an angle that's less than 90 degrees, and one that's an angle between 90 and 180. The best picture is one that I have not drawn myself, so I looked through the internet to find an example of the ambiguous case. We have 2 triangles, A, B, and C. And in the first example, you can see that all 3 angles are acute. A is less than 90, B is less than 90, and C is less than 90. However, if we were really solving this problem, there is another potential solution, which is labeled as A, B prime, C. And this is that ambiguity. Angle B can either be acute, putting it in quadrant 1, meaning it's less than 90 degrees, or angle B could be obtuse, meaning it's more than 90, and putting it in quadrant 2. And what changes is not the given angle C, but the other angle A, which would be smaller if B is in quadrant 2 and larger if B is in quadrant 1. And so we end up with 2 potential triangles, acute and obtuse, anytime the given information is an angle and 2 consecutive sides that aren't on either side of the angle, right? So if you were in geometry, you probably learned the theorems for triangle congruency, side, angle, side, angle, angle, side, and then you learned the non-existent one, angle, side, and that's how you remembered it. So angle, side given values are when we're going to have the potential for the ambiguous case. We're not going to see it in any other combination of given information. So let's take a look at this first example. How do we know if we've been given one angle and the 2 sides that are not sandwiching that angle? Draw yourself a quick picture. Oops, pretend that attached. A, B, C. Given one angle means there's an opportunity for the ambiguous case. That's not the angle we were given. Let's just fix that triangle while we're erasing. A, B, C. We're actually given angle C, so let's fix that. Now we're given side B, so this is in position to sandwich the angle here and here, but then we're given the side across from it. So you basically have the potential for the ambiguous case if you're given one angle and the side across from it instead of the 2 sides on either side. Let's set this up, let's solve it, and let's see if this is actually an example where the ambiguous case holds true. Because just because you could have the ambiguous case doesn't guarantee you do have the ambiguous case. Remember, when solving, you have the potential for 0 solutions, 1 solution, or 2 solutions. All of those can occur. With this setup, it looks like we need to find one of the other missing angles. So I have angle C and side C, and then I have side B. So I'm going to start this problem solving for angle B. Sine B, I'm still in orange, over side B is equal to sine C over side C. Multiply both sides by 28. We get sine B is equal to sine 24 over 25 times 28. That's 0.455554 actually no, That 4 would have to round up. So I'm going to dot, dot, dot here. Keep in mind, I'm not actually retyping this rounded in my calculator. I'm using the answer feature of my calculator to now take the inverse sign of that answer. So my first option for B is if B equals 27.1 degrees. Preferably, we're going to round that to the whole, but for this example, I am going to keep it with the tenths. Well, what is that answer in quadrant 2? To determine that answer, you're going to subtract it from 180. Okay, now we check if the ambiguous case is even valid. So I'm going to use orange for my first answer. B is 27.1 degrees. C was 24 degrees. Add those together and subtract from 180. Wait. 24 plus 27.1, 180 minus. We're going to get that angle A in this example would have to be 128.9 degrees. That is a valid measurement for angle A. For B prime, I'm going to switch colors. So let's use purple. Go Suns. We're going to do 152.9 plus our 24 that we were given, and we get 176.9. Subtract that from 180, and we find that A could also have been 3.1 degrees. Well, that's also a valid angle, albeit a pretty small one. This is an example of the ambiguous case. I have two potential solutions that I need to finish. For the first one, I've got angle B, angle A. I'm only missing side A. Now, if you look, angle A in this first example is obtuse and quite large. That means side A should be the longest side of 25 and 28. Set up our ratio. A over the 128.9 equals, the pair of sides I was given was C. So I'm going to use C over sine C because I know that has not been rounded. And I'm going to multiply both sides by sine of 128.9. So that gives me that side length A could be equal to 41.4, much larger than either of the other two sides. Finishing the second possible answer, I have side A prime over sine of 3.1. Now we're talking about angle A being ridiculously small, so I should get a side length smaller than either 25 or 28. I'm going to use the same ratio, sine 25 over sine 28, and this time I'm going to multiply both sides by sine of 3.1. And that does give me a smallest side of 2.9. So this is how we're going to get our solutions when solving the ambiguous case. And this actually concludes the video notes for Law of Sines. Thank you for watching.